Okay, and again, continuing on, just sorry for the pause break there, but I had to trim the video. So what we end up getting from this is 0.0159. Then we take the cube root of that value, so the cube root of 0.0159, and we end up with 0.25, and I'll just make sure that I get the exact value rounded. So we end up with 0.25, and then 0.2515, I'll round it to. Okay, awesome. So we've got our radius, and from our radius we're going to be able to work out what the size of the tin is. So now we can just check that we're differentiated correctly by constructing a sign diagram. And a sign diagram will tell us, again, whether this is a minimum or a maximum. And hopefully it's a minimum, because it means good news for us, we might even get a promotion from H2O Go. Okay, so in order to do this, let's just go to our trusty old calculator and plug in values to our derivatives. So 4 pi, again I'm just plugging in a value there, 4 pi lots of 0.1, yep, 0.1 is less than 0.25, so looking on this side, 0.1, and then we're going to have take, and then 0.2 divide by 0.1 squared. And we get a negative result, which is good. Because again, negative, it means that this could possibly be a minima, because it means it's decreasing there. This is going to be a minima, hopefully. And then it's going to increase again, so we might have the minimum total surface area here. So now we just take that and we plug in a value that's greater than this value here, 0.25. So let's see, I'm going to plug in 3, because 3 is greater than 0.215. So once I've plugged in 3, I get a positive result. And because it's positive, it means that yes, it's decreasing on this side, the slope's decreasing on our original function, and then on the original function it's increasing after this, so it means it's a minima, and it means we've found the spot where the total surface area is a minimum. So we know our radius. We've almost got our dimensions. We know our radius is 0.2515 meters, which also translates to 25.15 centimeters. So, you know, it's going to be a decent size radius. The actual thing, like the entire top of it in terms of its diameter, is going to be greater than a meter. So, you know, it's going to be a decent sized tank. It's going to hold 100 litres, and it's probably going to be reasonably tall too. But now we work out what our height is relative to r. So we just plug this equation into our calculator, and then we know what the dimensions of this will be. Okay, so fire up our calculator, and we have bracket 0.1, bracket, then divide by, then we put in bracket pi, and then bracket put in our radius, so 0.5215, bracket raised to the power of 2, bracket, and we get 0.5 meters. So 0.5 meters means that the height of this is going to be half a meter. So it's going to be half a meter tall, and it's going to have a radius of roughly 25 centimeters. So again, this is going to be almost half a meter across. It's going to be almost half a meter tall. So it's going to be a decent size, and it's going to hold around about 100 litres. So there we go. We found the lowest amount of surface area on this using derivatives, using calculus. We've been able to optimize the cylinder, again, so it has the ideal amount of resources, and it does take time to be able to get these optimization sort of questions and understand what they truly mean. But again, hopefully with a bit of practice you'll understand how to be able to work out what the formula is. Again, in this case it was just a simple volume formula. In other cases, it may be something more difficult. You may need to look at profit, you may need to look at triangles, you may need to look at Pythagoras theorem, you may need to look at creating all these different types of formulae. You know the formulae, it's just a matter of actually being able to apply it contextually, which is the difficult part, the part where most people get tripped up, including me, because sometimes I can't think of the formula that you need to use. However, Again, with a lot of practice, you'll be able to say, okay, I have a true understanding of this problem. I truly understand what's going on. And sometimes you may get a little bit lost with the formula occasionally, but just stick in there. Just think it through. Think, what is it I need to calculate? How do I construct that formula? And most of the formulas you already really know from previous mathematics. It's just a matter of actually putting it in the right context. So again, especially just touch up on your geometry, because that's a key part of optimization. But there's a walkthrough where we're optimizing the size of 100 litre can. Again, we're just using the first derivative. We're just finding that stationary point, using a sign diagram to check. And from that, we have optimized this H2O Go cylinder. So, hooray. That's pretty much all from me now. Practice your optimization. More videos coming soon. Any questions, any comments, please feel free to pass them on to me. And again, yeah, it's a pretty interesting topic of differential calculus. You can do quite a lot with it. Okay, that's all for now. See you later.